Okay, so today we're very happy to have Joao Silva from the University of Oxford, who's going to tell us about AdS Virasoro Shapiro from dispersive sum rules. So Joao, please take it away.
Thank you. Thank you for giving me the chance to talk about this work. So it's based on a paper that we put on the archive a month ago with Fernando Alday and with Tobias Hansen. So let me start by reminding you about the flat space Virasoro Shapiro amplitude. It's this function that you see here. It's a function of the two Mandelstam variables f and t. And let me tell you about the most prominent features of this formula, because then I want to compare it to AdS. So it has poles when each of the Mandelstam variables s, t, and u is equal to the masses of the exchanged particles. And the exchange particles, they are labeled in this way. So their masses are equal to 4n divided by alpha prime. And so, as you know, in this amplitude, there is an exchange of particles of higher and higher spin, spin 4, 6, 8, etc. But this amplitude has this feature that, despite this, the Regge behavior is soft. So the amplitude behaves in this way in the Regge limit. So the Regge limit is when you take t fixed and you take s big. And furthermore, it has this small alpha prime expansion. So if we expand it small alpha prime, it turns out that the coefficients multiplying the polynomials in S and T are zeta functions. It's another feature that we will see in AdS. Okay. Okay. So I just wanted to remind you of this. And now in AdS, we want to study an analogous quantity. So we will study n equals 4 superunion meals at leading order in the central charge. And we will take the 12th coupling to be large. Okay. And we will study this specific 4-point function. So the 4-point function is O2, which is the half BPS operator in the stress tensor multiplet. And we will study this 4-point function using Mellin amplitudes. So the 4-point function is, well, as you all know, a function TUV, where U is a conformal, U and V are the usual conformal cross ratios. And we will express this 4-point function through this integral. And in this integral, there are two independent variables, which are S and T, which are called Mellin variables. They are dimensionless. So before we had Mandelstam variables, now we have Mellin variables. And so in this integral, U and V enter in this way. And there are some gamma functions in the integrand. And there's a function M, ST, which is the Mellin amplitude. And this Mellin amplitude will be the object that we will study in the paper. Okay? So our goal is to calculate this Mellin amplitude. And so the AdS Virasoro Shapiro amplitude is the Mellin amplitude at finite lambda. Let's define it in this way. And this is what we want to aim at. We would like to calculate this function. Of course, this is at finite lambda, so this is hard. So we compromise with a more humble goal. And so we'll study this amplitude at large lambda. This is what we want to do. So any questions about this? There are a few people, so feel free to ask questions whenever you're confused. Probably not. Beautiful. So let me continue. Okay, so we will use Mellin amplitudes. So let me tell you something about this technique. So Mellin amplitudes, they are the analog of 3-level scattering amplitudes for anti-theta space. So they have the following properties. So they are crossing symmetric. Well, crossing symmetry is expressed by the fact that the Mellin amplitude stays the same when you interchange the Mellin variables in this way, just like for scattering amplitude. And it's a function, well, it's an analytic structure. It just consists of poles. So it has poles when S, T, and U are equal to tau plus 2m, where tau is the twist of an exchanged primary. So when you have a primary that is exchanged, in this case it's a super primary because we have n equals 4 supersymmetry. So when you have a super primary exchange, it gives rise to an infinite set of poles in this way, just like for scattering amplitude, the same happens when you exchange a particle.
So just so I'm understanding, the AdS scale here is being set to unity. So when you say poles, you mean relative to the AdS scale?
The AdS scale. I'm not sure I understand your question. The AdS scale is not set to unity.
So so ST and U have dimensions?
No,
so
they're dimensionless.
Dimensionless. So their momenta referred to what scale?
I want to think of ST and U as dimensional quantity. I don't want to think of them as momenta. I could say the same thing about the 3D easing model. I would say the exact same things about the Mellin. So take the 3D easing model. There's no AdS there, and I consider a 4-point function. Okay.
You might want to spell out more what ST and U are from your CFT
Yeah.
definition.
How are you defining ST and U?
In terms of conformal dimension.
Beautiful. So they are defined through this formula that you see here. So if you take this formula, would make sense in any CFT. Take the 4-point function and write it as an integral like this. Is that okay?
They end up conjugate to scaling dimensions, right? If I was to think of momenta and what they're dual to. I mean, at the end of the day, that when you compute the residues on these poles, you're computing the contribution of a particular operator with some scaling dimension. Is that right?
True.
Yeah. I don't know if that helps.
But I mean, the reason that the poles are spaced by integers is what?
Beautiful. So this is because, so consider this function TUV. It can be expressed as a sum of over conformal blocks. So if I consider the operator product expansion in one channel, let's say.
Yeah.
And so now let me think of the exchange of some primary.
Mhm.
It will contribute to TUV in the following way. It will come with U to some power plus subleading powers of U, of this variable U. And now you achieve precisely the same powers by having this function M having poles at these locations.
Are they the descendants?
Yeah, those the descendants. Okay, so the answer to my question is that the AdS scale has been set to 1 because the spacing of the descendants is the AdS scale.
I'm sorry, I don't really see what you mean by that.
Delta L naught equals 1 is raising the energy by 1 in units of 1 over R AdS.
True. Okay, what do you think?
All
Probably.
right. I don't want to hold you up, but I think I understand better what you're doing. So
Yeah.
thank you.
Thank you. All right, thanks. It's a good point. Okay, so this amplitude, as I was saying, is a meromorphic function. It has these poles, and it can be argued that it is bounded in the Regge limit in this way. So it decays with 1 over S squared. So this basically follows from causality in AdS. And so we want to use this fact. Now let me, for the specific case of the Mellin amplitude that we are considering, its first term, so there's a contribution to it coming from the supergravity Lagrangian, and for this reason the Mellin amplitude has this pole. And then there are stringy corrections, which are corrections in 1 over lambda. And in general, these stringy corrections are not known, and so our goal is to study these stringy corrections. So I just wrote in here the first 2 stringy corrections which are known. So the first one is this 120 zeta 3, and then the next one is this 630 zeta 5 times this polynomial, etc. And then the next one is also known, but then afterwards people don't know them. So our goal is to calculate these string corrections. Any questions on this, please?
Yeah, can I check the fall off of M as 1 over S squared? Is that a proven result or a conjecture?
It's a proven result.
That's a proven result. Okay, so for any reasonable CFT, we should expect that fall off behavior. I mean, does it have anything to do with gravity, or it's just a general property of a CFT?
It's just a general property of the CFT. For example, you can argue for here there's a slight technical complication because we are at large n, but if we are at finite n, you can just argue this from the operator product expansion. So
Good.
in that case, the basic argument is to say that in Lorentzian regime, the operator product expansion is bounded by the one in the Euclidean regime. So it's it's just a true result. Okay,
Is this the chaos bound?
this is the chaos bound for large n.
Wait, then why is it 1 over s square? Shouldn't it be s square or mod s?
It's because we have supersymmetry. So this I'm telling you that the
Oh.
fourth function is TUV, but I'm being
Oh, I see.
dramatic. Okay.
Mhm.
So these terms you showed, were they derived from strong coupling n equals 4?
This 120 is at the 3.
And yeah, and the next term?
They were derived from something called the flat space limit and localization.
So the strong Atuf coupling limit of n equals 4, was that used?
It was used in the sense that this theory is due to string theory. And no,
Yeah.
and for localization,
Okay. Because you gave us a formula for it in terms of a correlator and n equals 4, but that wasn't really used in getting this formula probably. Or was it? Maybe I missed.
which form are you talking about?
Formula at the bottom of this page,
Mhm.
did it come from the definition of M as a Mellin transform of the correlator in n equals 4 directly, or?
This result does not have anything to do with Mellin amplitudes. I'm just expressing the result using this language. Did this answer your question?
So, I mean, this looks like the flat space result. Is it?
Yeah.
Yeah. Okay, good. So it's exactly the flat space limit. So
It's exactly-
the ADS length
So
scale.
it's just based on a knowledge that you have to go into the flat space limit at strong coupling, at large lambda.
That's right.
So like the supergravity plus the R to the 4th looks like plus stringy corrections.
I didn't hear your question. Once again.
Yeah, I think.
No, I mean, what you've written down is like supergravity plus the
Yeah.
perturbative R to the 4th.
Yeah,
Yeah.
that's what it looks like to me.
Yeah,
It's polynomial.
It's just the definition starts off with an n equals 4 correlator,
yeah.
but I was just wondering if anybody ever uses that.
So I guess we can ask differently. The last expression here, is this coming from a string theory calculation or gravity calculation or from localization of n equal 4 on some?
So this first term came from the flat space limit of AdS, of saying that this correlator must be related to the Virasoro Shapiro amplitude in a certain way.
Yeah, okay, good.
This guy came from the same logic. And then there's this one. This one came from localization.
Okay, good.
Thanks.
Beautiful. Okay, so the paper is about stringy corrections, our paper. So as we've been discussing, I want to now summarize all that is known about the stringy corrections before discussing our paper. So as I was saying, there's this first term, which is the supergravity term, and then there are these stringy corrections. And now let me characterize them in the following way. So they are contact terms in anti-de Sitter space, so they must be polynomials in the Mellin variables, S and T. And these polynomials must be crossing symmetric. And so we will need a basis to characterize these polynomials, and we pick this basis where we define this polynomial sigma 2 and this polynomial sigma 3. Okay. So the corrections function the following way. Take sigma 2 to some power times sigma 3 to some power, which is just some general correction. It will appear in the Mellin amplitude proportional to the power of lambda, which basically follows from dimensional analysis. And the first coefficient is called the flat space limit coefficient, which is fully computable. People know all the alphas. And then there are corrections to this. The first correction we call beta, and then the correction next to that we call gamma. And these are the corrections that people do not know. People do know a finite number of these corrections, so they know precisely these ones that I'm telling you. They know this beta 0, 0, gamma 0, 0, beta 1, 0, and delta 0, 0. Okay, so this slide summarizes all knowledge about the string corrections that existed. I think it answers what you guys were discussing. Is this clear? This slide.
These are all alpha prime corrections.
That's right.
Or, yeah. So one of the corrections are invisible here, presumably, like G-string non-perturbative corrections in the amplitude.
So we are at leading order in G string. So
Yeah, good.
Just leading 1 over n.
Very good.
okay. Indeed, so these corrections will be invisible. This will correspond to loops in AdS. This is not we're studying. We're at 3 level. Okay, so this summarizes all the knowledge. And now I want to tell you about our paper. So I'll start by telling you the basic idea and then the main results that we obtained. And then I'll tell you about how we actually derive these results. And finally, I'll discuss some open problems, okay? Good, so what's the basic idea? The basic idea is to use the bound for the Mellin amplitude on the Regge limit. So, and this is better explained if we think about this at finite Toff coupling. So let's think about the Mellin amplitude at finite Toff coupling. And as we saw, we have the stringy corrections, which have higher and higher powers of the Mellin variables. But these stringy corrections, they cannot be random numbers, so they must be numbers that are in such a way that after you sum and you consider the Mellin amplitude at finite lambda, this bound is obeyed. And so this will place strong constraints on what these stringy corrections can be. So this is the idea that we want to explore. And we'll explore this through a dispersion relation. It turns out that it's convenient for us to introduce a subtraction. So we will introduce a denominator here. This will be useful. It's not clear now, but it will be clear later on. And you can write the Mellin amplitude as an integral. So consider a generic point and write it as an integral around its point using Cauchy's theorem, according to this picture. Now take this contour and now blow this contour to infinity. And when you do that, the arc at infinity does not contribute due to the bound on chaos. And so there is just, and so you can re-express this Mellin amplitude as a sum over the residues of the poles of the Mellin amplitude. In this way that you see here, okay? And each of these residues is proportional to the OP coefficient of the operator that is exchanged, and then the rest of the residue just you can compute it from it depends on something called Mach polynomials, which are basically the analog of conformal blocks. So the point is that this omega that I'm showing you here is known explicitly. It's a complicated function, but we know it explicitly, and we can just calculate it whenever we want. So this will be the basic tool of our paper, that you have the Mellin amplitude, you divide it by this denominator. There is a number q that appears that will be an integer number q that will be useful to us. And you can write the Mellin amplitude as this. Okay. Any questions about this? So we'll use this tool. And this is called a dispersion relation. So, as you guys know, it's called a dispersive summary. Okay. So we want to use this tool, and as I was saying, we are working at, so we were thinking about this at finite lambda. But now let's take lambda to be a huge number. When we take lambda to be a huge number, then the left-hand side is very well approximated by the formula that I've shown you before, which captures these stringy corrections. And then on the right hand, so in particular, the left-hand side organizes itself into powers of 1 over lambda. And so on the right-hand side must be that the conformal data that appears in here will also organize itself in powers of 1 over lambda in such a way that this equation is obeyed. So this is something that we will explore. And so in the operator product expansion, there are the 3 classes of operators. There are the so-called protected operators. So we know everything about them because people have studied type of operator expansion very, very well. So there are the protected operators, we know everything about them. There are so-called double trace operators, so when you take these 2 operators, O2, you can fuse them together, and then you have double trace operators. And then there's another class of operators which are very heavy, and which we will call string operators. And these are the ones that will be the main players in our work. Okay. Good. Okay. So now I want to tell you our main result. But before telling you our main result, I need to tell you about something auxiliary. So we will derive from our sum rules that the data, the CFT data of the stringy operators can be organized in this way. So the twist starts at lower order lambda to the power of quarter times the function tau 0, and then there are corrections to it. And for the OP coefficients, they will obey this formula. So in particular, they will decay exponentially with 1. We'll derive this, and they can be expressed by a function f, which starts at order lambda to the 0. Just some facts that I'm stating, they are useful to state the main result. And now the main result is that for each coefficient in the Mellin amplitude at strong coupling, for each coefficient, there is an equation that relates it to the CFT data of the stringy operators. So let me show you the simplest of these equations. Take one of the flat space coefficients, let's call it alpha A0. And this is actually an infinite set of coefficients because this A can be 0, 1, 2, 3, etc. So take all these coefficients and we claim they can be written as a sum for all the stringy operators. And in the numerator, you will have the OP coefficient at leading order, and in the denominator, the twist at the leading order. The twist is the conformal dimension minus the space. Okay, so this is a good time to pause for questions. Is the main result clear? Any questions about this? Okay, so good. Let me tell you about the structure of these equations. So the equations their structure is the following. So for the simplest of these coefficients, the simplest are the flat space coefficients, and they only involve the OP coefficients at twists at leading order. And then for the next correction, you will need the OP coefficients at twists at the subleading order, and so on. So then if you have the equation for gamma, it will involve F4 and tau 4. And so we should contrast this with the conformal block decomposition. So now you might ask, why did we not see this before with conformal blocks? The point is that the conformal block decomposition is not sensitive to stringy operators. So people have been using the bootstrap to study diagrams in AdS for a long time. And if you decompose a contact diagram into conformal blocks, you will just see double trace operators. But here we are not using conformal blocks, we are using dispersion relations. So that's different because we expand into channels and we also use the bound on chaos. And so it turns out, as we'll see, that these dispersion relations will be sensitive to heavy operators, which the conformal block decomposition is not. Okay. Okay, so we formulate these equations. Now I want to tell you what we can derive from them. So let's start solving the equations. And so one thing we can do is to plug what is known about the flat space coefficients, and then to see what we can derive about the CFT data of the string operators. So this, for example, the first of these coefficients is called alpha E0, and it's just a zeta function. And then the next one is a product of two zeta functions. That's what this zeta means. It's a multivariate zeta function, and so on. Okay, so we plug these alphas and we use it to solve for F0 and tau 0. What are our results? So one result is that the twist of the stringy operators is quantized. So the string operators cannot have any twists. Their twists must be equal to 2 square root of delta times 1 to the power of quarter, where this delta belongs to is a natural number. This will follow from our dispersion relations. And furthermore, the OP coefficients F0, we can also determine all of them, and they will obey a set of equations that I will show you. For example, let me show you the simplest of these. So, for example, the F0s obey this equation that I'm showing you, and the next equation is this one, and so on. Okay, and so this is a rederivation of an ancient result by Gupsa, Klebanov, and Polyakov, who studied short strings in AdS, and they already knew about this. But the advantage of with our work, you can study subleading corrections, and in particular, these operators, as I was going to tell you, they lie in Hessian trajectories. So they are characterized by two quantum numbers, delta and L. Delta labels the twist. So for example, if you take delta equals 1, then the operator must have spin 0. If delta equals 2, it can have spin 0 and 2. If I have delta equals 3, it can have spin 0 to 4, and this will also follow from our dispersion relations. Finally, we also study corrections to the flat space limit coefficients. So in that case, our logic needs to be different because we cannot. So in that case, what happens is that we have the Mellin amplitude, we have some coefficient in the Mellin amplitude equals to the CFT data. In general, we don't know the CFT data and we don't know the coefficient in the Mellin amplitude. So what do we do there? What we do is we make a guess for what the coefficient of the Mellin, coefficient in the strong coupling expansion of the Mellin amplitude can be. This is using the so-called uniform transcendentality. So you can write these coefficients in terms of a finite number of parameters. And then you can fix all the parameters because there are some constraints for localization and integrability. In this manner, you compute an infinite set of corrections to the flat space coefficients. So this A can be 0, 1, 2, 3, etc. And you can calculate this formula that I'm showing you.
So, okay, I'm still, I think, obsessed about the same question. So this is again things whose dimensions are, the spacing is again the AdS scale and not the string scale. Is that right? The horizontal axis? I'm just trying to understand, so like in what sense they're stringy. So there are two scales in the problem, right? There's the AdS scale and there's the string scale. And lambda is basically the ratio of the AdS scale to the string scale.
Yes.
And so the sort of resonances that you see in the flat space Veneziana formula, they're spaced by the string scale, well, the momenta relative to the string scale, basically. And those correspond to the oscillator towers. But the recurrences that you're talking about here as stringy operators, they're being spaced not by lambda, right? They're being spaced by the AdS scale?
They are being spaced by the AdS scale, you can set it to 1. So if you set the AdS scale to 1, this lambda just becomes 1 over square root of alpha prime or something like this. And so you can think of it like that, just like you would think about the masses of the.
That's right. That's right. So again, the horizontal axis, when you say 1, 2, 3, 4.
In these units.
That's relative to the.
In these.
Yeah, that's the twist, right? So it's.
So this tau starts at lambda to the power of quarter. I'm suppressing this lambda to the power of quarter.
Right. Ah. Okay. I see. Okay, thank you.
Beautiful. Any other question? All right. Okay, so these were our main results. Now comes the part of the derivation. So I'll tell you how did we actually derive that. Okay, so as I was telling you, we want to study these stringy corrections. So we better understand the supergravity correlator first using the dispersion relations, and then we'll go for the more complicated stuff. So for the supergravity correlator, we want to analyze this equation. And for M, we plug on the left-hand side this expression for the correlator. That's well known, that has poles. And so in this case, on the right-hand side, what should we put? What we should put there, the short multiplets. And as I was telling you, everything is known about the short multiplets. So they have twist 2 and spins 0, 2, 4, etc. And their OP coefficients have been calculated. And so we can understand the right-hand side, it's given by this series. And as to the double trace operators, well, now we need to make use of a property of our function. So our functional, so the double trace operators have the following twist. They have their twist is 4 plus 2n plus 1 over 6 anomalous dimension. Okay. And the function is such that it vanishes precisely when the twist is 4 plus 2n. So the contribution of the double trace operators will come proportional to their anomalous dimensions. So it will come proportional to the derivative of the functional times the anomalous dimensions. And the anomalous dimensions come with order 1 over c. Well, I'm also studying the Mellin amplitude at order 1 over c, so I always keep this in mind. So that's why the contribution is not 0. And it turns out that for this parameter cube controls which families of double trace operators contribute. So only the first few families will contribute. It turns out to be this way. Okay, so these anomalous dimensions, they are fully computable. People computed them from the bootstrap. We can also compute them using the dispersion relations. And they are given by this infinite series. So basically at order 1 over lambda to the power 0, we know everything because we know all the operators exchange and we know the Mellin amplitude and things work. Okay, so this was just to set up our dispersion relation. Any question about this? Okay, so let me tell you some more about the double trace operators. So let's consider some general contact term that appears in the Mellin amplitude, and we can write it like this as sigma. I'll take now some example, which is sorry, let me say again. Let me consider an example of a contact term, and I'll consider just sigma 2 times some coefficient kappa divided by lambda to the power 5 halves. I'm just considering some general example, some examples which I want to work out. Okay, so consider this example. And the anomalous dimension comes proportional to kappa divided by lambda to the power 5 halves times gamma tilde, and gamma tilde will be some number. Okay, and it turns out that only a finite number of anomalous dimensions are non-zero when you consider some specific contact term. So if you consider this contact term, it will turn the anomalous dimensions of the scalar and of the spin 2 operators. Well, the anomalous dimensions will be non-zero, but for the other operators, they will vanish. And so this gamma tilde, it can be calculated from a dispersion relation. So suppose that you put on the left-hand side in the Mellin amplitude sigma 2, and then on the right-hand side, you put the double trace operators, and you put their anomalous dimension. And now you consider this equation. So as I was telling you, we know the omega. So you can just take this equation, write it explicitly, and then you can calculate the anomalous dimension. And you find that gamma tilde is equal to this minus 64. And this gamma tilde 02 is equal to this other number, etc. We can calculate all the anomalous dimensions. So why am I showing you this example? Because in order to write a dispersion relation, we had to pick q bigger or equal than 2. Let's appreciate this fact, because so on the left-hand side, if q is bigger or equal than 2, then you can write a dispersion relation and the arc at infinity vanishes. But if q is equal to 1, let's say, then this object does not vanish at infinity. So you cannot write the same dispersion relation. Okay, so you need to have q bigger or equal than 2 to derive these anomalous dimensions. Of course, the method that you use to calculate the anomalous dimension is not important. So you can also derive it from conformal blocks. I just want to make the following point, which is suppose that you now take q equals 1. Okay, suppose you take q equals 1 and you consider that contact term that we were studying. You can now consider this difference. So you consider the Mellin amplitude minus the double trace operators, and this does not need to vanish. Indeed, this does not vanish, and it turns out to be equal to something non-zero, which is this minus 2. And so we can derive a general conclusion from this, which is from this example, which is that just with double trace operators, we cannot satisfy the dispersive sum rules. Okay, so we wrote down a dispersive sum rule. We know that it's true based on general arguments, and we plug there the operators that we knew, which were the protected ones and the double trace operators, and they are not enough. So what other operators can we put there? Can we put into the dispersive sum rules?
Actually, before you, so you have a complete. Well, does this completely characterize double trace operators that don't get anomalous dimensions? Do you have a complete list of what is protected among double trace?
No double trace operators are protected.
No double trace operator. Everyone is getting a correction.
Yes.
Well, that's interesting. Okay.
And for the double trace operators, we know. So the logic is the following. the double trace operators, they have these OP coefficients. This just follows from the supergravity correlator. Now, if you consider contact diagrams, they will induce anomalous dimensions on this quantity. Okay. So these are the operators that we're talking about. Does that help?
Yeah, I'm actually surprised there's nothing that stays protected at low dimension. Okay, very good.
Okay, so we consider the protect operators and the double trace operators, and they are not enough to satisfy the dispersive sum rules. But these are all the operators that have, let's say, low energy. Or that have small twist. So it must be that there is something which has a very large twist that makes the sum rules correct, because if we think about all the low twist operators, we already listed all of them and we took them all into account. So there's a general conclusion is that the dispersive sum rules must be sensitive to UV physics, to operators in the UV. Okay. And so this is what we want to exploit. So, okay, before we go on, any question about this? This is something to take from this talk. Any question about the statement? Yeah, I'm just saying something here. Consider the operators with low twist. They are the protected ones in double trace operators, and the rest is heavy. And I'm just saying that the low energy stuff is not enough. Okay, so we want to study these heavy operators, but before doing that, I want to package all the information about the low energy operators. Let me package it in this way. Take the Mellin amplitude minus two double trace operators, minus this sum, and now this is the sum that we can do. So I'm telling you that if you do the sum, then the first contribution will start at order lambda to the power minus q minus 3/2. Q was this parameter that we introduced. And then the next one will come at order lambda to the power minus q minus 2, etc. And then there are some coefficients, which are these alphas and betas, and the alphas and betas are defined by this formula that you see below. Okay, so yeah, we can package this information in this way. Okay, so now let's consider the heavy operators. It just follows from scaling arguments using effective field theory that if, well, we have a scale alpha prime in our problem. So the new physics must start at energy 1 over square root of alpha prime, and if you translate it into lambda, and if you then it's equivalent to the statement that these new operators must have must start at lambda to the power a quarter, and then there is a number tau 0 that we will determine. Okay, so consider these operators and their twist started to the lambda to the power 1/4 plus corrections. And so the twist is very large. So we need to exploit our functional for when the twist is very large. And it turns out that when the twist is very, very large, then the functional obeys this formula that you see here. This is something that we can calculate. Good. And so now we can learn something about the OP coefficients of the string operators, because if you consider the OP coefficient squared, the OP coefficient is c squared. So if you consider this c squared times omega, then it behaves in the way that you see here. This is the right-hand side. And then on the left-hand side, it must match the low twist operators that I mentioned before. And as I was mentioning, they start at order lambda to the power minus 3/2 minus q. So this formula must be true. So you obtain that the OP coefficients of the string operators start at this order. They behave like this. And so in particular, you derive this formula. That the OP coefficients must be equal to this formula that you see here, where f starts at order lambda to the 0 plus some leading corrections. For the twists you have this. Okay, is it clear, the logic?
Yep.
Beautiful. Thank you for saying something. Okay. So okay, so in this slide, so I just want to make this point that If you consider the low energy operators, you can write them in this way, and there are coefficients alpha tilde and beta tilde. I already wrote this equation. There are coefficients alpha tilde and beta tilde that come from the strong coupling expansion of the Mellin amplitude. Concerning the stringy operators, we can organize their contribution in this way, where this alpha hat depends on the data of the stringy operators, and the same thing for the beta hat. And now we match the two things, and we obey this, and we obtain this set of equations. So alpha tilde is related to this alpha hat in this way, and so on. Okay, so this is our main result, and now we want to explore these equations. Okay, so as I was telling you, the simplest equations are the flat space limit equations. So let's study the first flat space limit equation. So remember that on the left-hand side we have alpha, and then on the right-hand side we have the data of the string operators. Now I'm using here that the first coefficient alpha A0 is zeta computed at 3 + 2a. This comes from the Virasoro Shapiro amplitude. So we have this equation, and we want to obtain information about f0 and tau0. And it turns out that it's very useful to take this the limit a goes to infinity. So when you take a goes to infinity, then this zeta just becomes 1. And on the right-hand side, notice that f0 and tau0 need to be positive due to unitarity, because f0 is an OP coefficient and tau0 is a twist, so they need to be positive. And so on the left-hand side, and so on the right-hand side, the leading contribution when you take AB is given by the operators with the minimum twist, so which I highlighted here, times the sum of their OP coefficients. And so the only way for this equation to be satisfied is if the minimum twist is 2, and if the sum of these OP coefficients f0 gives 1. The only way for this equation to be satisfied. And then we can push this idea further. So the zeta function obeys this expansion. And so if we match it to the right-hand side, it must be that the twists are given by 2 square root of delta times lambda to the power of 1. Okay, any question about this? Okay, so I cannot tell if this is super clear or not. Okay, good. So for the what are other things that we impose? So I inputted one class of constraints from the flat space limit. I will now impose other constraints from the flat space limit. So suppose that I consider all the equations involving the alpha AB. Then for each delta, the only allowed spins, it turns out, are 0, 2, etc., up to 2 delta minus 2. This comes out of our equations, but I'm not showing. And we can calculate all the OP coefficients, and they obey these formulas. So there is an FM0, which is given by the sum of OP coefficients, and the sum is equal to this function W, which obeys a recursion relation. So the W0 is 1, W1 is the harmonic number, and then W2 involves the harmonic number of degree 1 squared plus the harmonic number of degree 2. And then W3 will involve the harmonic number of degree 1 to the power 3 and the harmonic number of degree 3, and so on. So that's the structure of the equations. Okay, so these are our results about the flat space limit coefficients. And some of these OP coefficients were already known. So I want to tell you about 2 more of our results. So one result concerns the structure of these stringy corrections. So consider a contact term like this that appears in the Mellin amplitude. So let me write the coefficient that's multiplying it in this way. It's convenient to have some gamma functions. And the coefficient is basically this psi AB. So in principle, this psi AB is defined for A equals 0, 1, 2, etc., and for B equals, and when B is a natural number also. Now, from our sum rules, this psi B turns out to be equal to a series in this way, where P is a polynomial in A that depends on the conformal data. And that delta is this parameter that you see here that is being summed. And now notice the following, that this formula makes sense for A in the complex plane, because this formula makes sense when the series on the right-hand side converges. And then when the series does not converge, you can define the analytic continuation. So this is something that we didn't know without the sum rules. And furthermore, it turns out to be very instructive to consider the case where A is negative. So suppose that A is negative. A priori, this does not make sense because you have no negative terms. You have no negative powers of sigma 2 in the expansion of the Mellin amplitude. But anyhow, so we can consider A negative and consider the analytic and consider this when A is negative, psi AB is given by this series. And then if you look at our dispersion, at our dispersive sum rules, it turns out that terms like this appear, terms that appear on the right-hand side, and when they appear, the left-hand side vanishes because you cannot have negative powers of sigma 2. And so we derive this conclusion that this psi AB vanishes when A is negative, but it does not have, it has a finite set of zeros. So it vanishes when A is equal to minus B all the way to minus 1. And we think this might be very useful to bootstrap this theory. So suppose I consider, say, psi A 1000, and claim that this function has 1000 zeros. Anyhow, that will be so this function has 1000 zeros, but there are, in principle, it will involve a product of 1000 type of functions. So there are many parameters to fix. But anyhow, we think this type of condition will be useful. And this leads to non-trivial equations. For example, this is a non-trivial equation involving the OP coefficients of the string operator. Okay, good. And another thing that we study is the first correction to the flat space coefficients, which are these betas. So I want to show you, I just want to show you this conclusion. So this beta turns out to obey this equation, which looks a little complicated. Well, in this equation, F0 and T0 are things that depend on the data of the string operators. And there is an harmonic number that appears. So this H is an harmonic number. So now we make the following guess for F0 and tau 0. We guess that they are made up only of the functions that enter the equation. So if we have an harmonic number that enters the equation, then F0 can be equal to the harmonic number, but we say that it cannot be equal, let's say, to the harmonic number squared or to the harmonic number of degree 2. Okay. So this is so-called uniform transcendentality. So we make this ansatz for F0 and T0. It's an ansatz in terms of 4 parameters. And then a few of these betas are known from localization. And it turns out that a few of these taus are also known from integrability. And so in this way, we can fix all 4 parameters and we determine beta is 0. This will be the first correction to the flat space coefficients. Any question about this? Okay, and so this was a talk, so let me just list some results. So these operators are expected to be degenerate, and we can study this degenerate by studying other correlators in this way. It would be cool to study operators that are heavy but that have large spin, and to my knowledge, it's believed that their dimensions should grow with the logarithm of the spin. We can probably study them using dispersion relations. If we had data about subleading Regge trajectories, this would be very useful to study the Mellin amplitude. And furthermore, this technique should be applied in other examples of AdS CFT, for example, in BGM theory. All right, thank you.
Joao, have you tried to use, recently there was this work about using SL2Z harmonic analysis to try to derive some constraints on the scattering amplitude of, I guess that case was some correlators in n equals 4. But I was wondering if you can combine your results with those to sort of constrain more of the amplitude.
I haven't thought about it, but that sounds interesting. It would be cool to have an idea of the type of functions that can appear at the level of the stringy corrections. If we had that, that would be really useful to constrain the CFT data a lot. But I haven't thought about that.
Can you show again the operators that got you said the twist or quantized or like this heavy operators?
Yeah.
With dimension, the twist grows as a lambda to the 1/4, is that right?
That's right.
Oh.
This thing. Yeah, this was pretty unexpected for us. But then when we use the flat space coefficients, that this need to be quantized.
Do you have any understanding of why that is?
They are two what's it called, short strings in AdS. So their masses are like n divided by, so the mass squared is n divided by alpha prime. And so in CFT language, it's like saying what I'm saying here. So this is what they were saying, Gubser, Klebanov, and Polyakov. That would be their meaning.
Well, if there are no more questions, let's thank Joao again. Let me stop the
Thank
recording.
you.